Good morning. Originally, I had meant to call this Funky Town and play a little clip from that song, although I think I would get copyright struck into oblivion if I did that. So we will move to Curvy Town. We no longer have a flat space or a flat surface. We have some sort of curved arrangement. The thought is that we have points within this curved surface. A scalar field is a function that for each point of the surface gives you a number back, a frame invariant number, no coordinates needed. Of course, once you have the idea of a scalar field, you can think of drawing curves where some scalar function is constant. We could call those coordinates, as we've done before. As previously noticed, we can't draw an arrow on a curved surface, but I can draw curves of constant function value and construct the one form, the gradient one form, that goes with that function. It's just partial of the function with respect to the first coordinate and the partial with respect to the second one. As I move along the curve in my surface, I encounter different x1 and x2 values. The phi changes with respect to those variables, so this actually makes sense. I'm going to think of this as a member of the space of one forms. A picture for d tilde phi at p, you remember from the first semester, is this kind of picture. So at least for now, we've given up the idea of vector as an arrow, and we've replaced it with the idea that, locally at least, a one form is a kind of grating. Our archetypal one forms are these gradients. If I think of component number alpha of the one form that I get by taking the gradient of phi, then phi alpha is just partial of phi with respect to x alpha. Not doing anything fancy, just using the chain rule, if I were to use other coordinates, phi mu bar would be partial of phi with respect to x mu bar. Then the chain rule for variables says that this is partial of phi with respect to x alpha times partial of x alpha with respect to x mu bar. But this second quantity is what we've been calling lambda alpha mu bar in the case where we don't necessarily have flat coordinates. The observant will see this is the same transformation law that components of one forms obeyed back in the first semester. Likewise, we will construct a basis for the space of all one forms. Omega tilde alpha is going to be the gradient of the function x number alpha. So omega tilde 1 will have components partial of x1 with respect to x1, partial of x1 with respect to x2. x1 and x2 are independent variables, though, so this number works out to be 1. This number works out to be 0. Likewise, omega tilde 2 has components partial of x2 with respect to x1, partial of x2 with respect to x2, and you obtain the components for omega tilde 2 to be 0 and 1. These kind of thoughts are true regardless of how you specifically set up your indexing. Any one form, thinking of its components, can be thought of as a component times a basis element. If you look at the mathematical formulas, this is the exact same argument that we did back in the first semester, though we started off thinking about vectors first there. Since the phi can be any one form whatsoever, we can figure out something about the quantities inside the bracket by picking the phi correctly. This is a sum, though, over alpha, so I can't just divide the phi alpha out. But the same argument as in the first semester leads to the same conclusion. The basis one forms transform in the same way as they did in flat space. The components of a one form transform as they did in flat space. For details, of course, you could let, for instance, phi tilde, the one form phi, to just be the first of your basis one forms. The calculation then says the quantity inside the bracket must be 0, and by doing this with the other basis one forms, you can come to the conclusion that all of those numbers inside the bracket must be 0, so that must be true. In the first semester, we defined the one forms to be members of the dual space to the vectors. We have first defined the one forms here, so now we'll define vectors to be the linear functions of one forms into scalars. As before, if I want to think about the components of a vector, I will feed basis elements into the function v. In this case, v alpha will be v evaluated at omega tilde alpha. We have to have a basis for the space of vectors, so we'll define it in the way that we did in the first semester, except the other way around. E alpha is going to be that special vector, that special function of one forms into scalars that does this. If I take E alpha and I feed one of the basis one forms into it, I either get 1 or 0, depending on whether the indexes are the same or not. The omega tilde alphas and the E betas are coordinate bases. In the first case, for the space of one forms, in the second, for the space of vectors. Using the linearity, it's easy to see that v evaluated at p is still p alpha v alpha. Likewise, we define p tilde at v to also be p alpha v alpha. These are scalar quantities. I could express them in one coordinate system or another. P alpha v alpha must equal p mu bar v mu bar. In the first semester, we knew how the mu bar transformed and used this fact to figure out how the one-form components transform. In this case, the one-form components come from the chain rule, so we know that p mu bar is lambda alpha mu bar p alpha. We will use this to determine how the components of the vectors transform. If you go through the details, everything works the way it did in the first semester. You eventually find out that v beta is lambda beta mu bar v mu bar, and then doing the usual manipulation, you find out that v nu bar is lambda nu bar beta v beta. These are the same formulas as in the first semester, even though we are no longer in a flat space. In the first semester, we figured out how to do covariant derivatives based on very general principles. In the first semester, we had v mu semicolon nu is v mu comma nu plus lambda mu alpha nu v alpha. Also, p alpha semicolon gamma is p alpha comma gamma minus Christoffel lambda alpha gamma p lambda. The Christoffel symbols were defined to be the coefficients of the basis vectors in the expression partial of E alpha with respect to x beta, for instance. We will define them the same way. In the first semester, we were able to get a formula for those Christoffel symbols in terms of the metric. How did we do that? Firstly, we convinced ourselves that the covariant derivative of the metric tensor was 0. This fact turns out to be the key to the argument, and in fact turns out to be extremely important to us in terms of local flatness. Every index that is like a vector index has a plus Christoffel variable term. Every index that is like a one-form index has a minus lambda variable quantity. So if a person were to just write out the covariant derivative of the metric tensor, you'll have the ordinary partial derivative, and since you have alpha and beta, there are two terms because you have two one-form like indexes. In the first semester, we wrote that formula down 3 times, rotating and shifting the indexes each time. Then we took 2 of the formulas and added them together and subtracted the third one. After a mess of algebra, in the first semester, we were able to figure this out. We were able to state the Christoffel symbols in terms of the metric, which in turn will let you figure out the geodesics and all manner of interesting quantities. I need to recover this in the case that I am not in a flat space anymore. What I have to do is I have to convince myself that this statement is true. If that's so, the same mathematical formulas that worked in the first semester will work in the curved case. How did this work in flat space? In Cartesian, all of the Christoffel symbols are 0. That's because the basis vectors are constants. So if you differentiate a basis vector with respect to x gamma, you get 0 times z0 plus 0 times z1 and so on. So all of the Christoffel symbols are 0. In Cartesian coordinates, then, to do a covariant derivative is the same as doing the ordinary partial derivative. On the other hand, in Cartesian, all of the components of the metric are constant, so g mu nu comma gamma is 0. But in Cartesian, comma is the same as semicolon, so this says if you use Cartesian coordinates, you can conclude that g mu nu semicolon gamma is always 0. But see, that's a tensor equation. If it's true in one coordinate system, which it is, Cartesian, then it's true in all of them. That's how the argument went. To keep this from being too long, I'm just going to state this. I may make another video about it, though. I've written the argument up, a nice argument, but this isn't a good place to do that. So I'm just going to state this. Local flatness theorem. Give me a point of your space. I can always construct coordinates so the partial derivatives of the metric at that point are 0. When I say at that point, though, I really mean it. Move slightly away from point P, and the partial derivatives need not be 0. Even though I can no longer say a vector is an arrow, the metric tensor was defined to be the dot product of two vectors. So take g mu nu equals e mu dot e nu and differentiate partial differentiate with respect to x gamma, apply the product rule. The Christoffel symbols were defined to be the coefficients of the basis vectors in derivatives like this, so I can just write this formula down. Remembering that E alpha dot E nu is G alpha nu, and E mu dot E alpha is G alpha mu, I can express this in terms of the metric. Notice I didn't say anything about Cartesian coordinates because I don't need to. We're going to do the same manipulation that we did in the first semester, except my symbols look different now. We've just figured out that this fact must be true. If you pull gamma off the end and put it at the beginning, and then put the comma on the last index, you get this one. If you rotate it again, you get this one. And just like in the first semester, we're going to add the first two together and subtract the third one. In terms of the components of the metric, this must equal all of this. Then a miracle happens. If you look at the first term, that one, and if you look at term number 6, 1, 2, 3, 4, 5, 6, I have a Christoffel symbol with an alpha upstairs, gamma and nu downstairs, gamma and nu downstairs. The Christoffel symbols are symmetric on the bottom two indices. I didn't prove that specifically in the case of a curved space, but the argument's exactly the same as it was in flat space. Also, the fourth and fifth terms cancel out. 1, 2, 3, 4, alpha, alpha, gamma mu, mu gamma, alpha nu, alpha nu. So out of all of those terms over on the right, only two of them don't cancel out automatically. Over on the right, I have mu and nu, nu and mu. Because of the symmetry on the lower two indexes of the Christoffels, those index pairs are the same. Upstairs alpha, downstairs alpha. Upstairs alpha, downstairs alpha. Gamma, gamma. The two terms over on the right are the same. And then, not to make this story longer than it needs to be, look back in your notes from the first semester, do exactly the same manipulation, and you arrive at this formula. This is the same formula that worked in flat space with curved coordinates. Previously, in special relativity, when we wanted to do some calculation, we would frequently construct a momentarily co-moving reference frame. This was the case either in Cartesian or Minkowski coordinates. We're back in business now. In your curved space, select a point P, construct a locally flat coordinate system at P. Since the partial derivatives of G at P are all 0, our nice formula tells us all of the Christoffel symbols are 0 as well. At P, G alpha beta semicolon gamma is the ordinary partial derivative minus a Christoffel symbol that is equal to 0 multiplied by something, minus a Christoffel symbol which is 0 multiplied by something. I get that I must have 0 there. The reason I want to be so emphatic about that is In a locally flat coordinate system at P, then, G alpha beta semicolon gamma is going to be 0, which is what I want. Point P was arbitrary. This is a tensor equation. If it is true in my locally flat coordinate system, it is true in all coordinate systems. So these locally flat coordinate systems are the ones that are going to play the role of our nice coordinate systems back in special relativity. The Cartesian, if I'm doing Calculus 3, or the Minkowski. What this says is, locally, at a single spot, there's a way of changing the frame of reference so that at and close to that spot, the space-time looks very much like that of special relativity. To be exact and quantifiable, I mean the covariant derivative of the metric is 0.